Today we're going to talk about objects that are experiencing free fall, and these objects in particular are going to be thrown straight up into the air, and because of gravity they are then going to fall straight back down. So before we get into the specifics of today's topic, which I like to call up and down because that's what our object is going to do, let's take a little bit of time to just review some facts that you should have learned up until this point about objects that are moving vertically through the air. So originally we talked about objects that are in free fall where they are dropped. They start at some position above the ground. We let go of the object. Most of our objects are going to be on Earth, so let's just assume that we're talking about an object on Earth. And so if we let go, there is a gravitational pull coming from the center of the Earth that's going to cause the object to accelerate downward towards the Earth's surface. And so when we talk about objects that are in free fall, this is the only thing that we are going to consider as far as what is affecting our object and what is responsible for how that object experiences its motion. So it says here on the first bullet that our objects will be affected only by gravity. And I feel like this is really the only statement that needs to be made, but sometimes interpreting what that means could use a little bit of clarification. So when we say only affected by gravity, that means that we are not going to have any other factors, at least for right now, that are going to play a role in determining how my object is going to experience its motion. So on the next line, when it says neglecting air resistance, your real life experience has probably allowed you to see some sort of object that kind of floats or flutters as it falls. Think, for example, of a piece of paper that you have dropped, and you'll see that it kind of floats right, left a little bit as it slowly falls to the ground, whereas if you take some sort of solid object like a rock and drop it, it's just going to go on a straight line down towards the ground. So when we are asking you questions about the object's motion, about how it accelerates, or anything like that, I want you to interpret all objects as if it's that very dense solid rock that is falling. So if we are talking about neglecting air resistance, if we pretend that there is no air, or if we take our object and put it inside of something called a vacuum is some sort of environment where we have all of the molecules removed, therefore there is literally no air resistance. If I were to take my piece of paper and my rock and put them inside of a vacuum or some sort of environment where there are no air molecules there to interfere with it, then when I let go, both of those objects are going to fall simultaneously and hit the ground at the same time because we are affected only by gravity. So this means no air resistance. Now we have found, or scientists have found, that there is a steady rate. All objects, it does not matter if it's the rock or the paper or a person or a car or whatever that object may be, if I take that object and I allow it to be affected by gravity and nothing else, all of those objects are going to experience the same acceleration rate. So just to review, acceleration is the rate of change in velocity over time. So when we say that the acceleration due to gravity is a negative 9.8 meters per second squared, what this means is that my object is going to change its velocity by a value of 9.8 meters per second for every 1 second of time. That's what the word acceleration means. This is a negative value because the acceleration is directed physically downward towards the ground, and so we are going to identify that as the negative direction. So any questions, any math work that you perform in this class where we are including the effect of gravity on our object's acceleration, we are going to plug in a value of negative 9.8 meters per second squared. So these are some of the basics that you should already know. So let's talk now about objects that go up and then come back down. You've probably heard the phrase, what goes up must come down. And so these objects are going to be sent in the upward, think vertically up towards the sky direction. And so we're going to send our objects up in the positive direction, but we are still going to have gravity act on it. Think about it. As long as we are on Earth, gravity is there. Gravity is not going to go away if we are on Earth. In fact, we would have to be in far outer space where there are no large bodies of mass that are going to have a gravitational pull on us, okay? So we're going to assume that there is gravity unless the question tells you differently. So it says here that the gravity is going to work to accelerate the object in the negative direction. So remember, we've identified acceleration could be positive or it could be negative. So here is a situation where we have an object that is moving up in the positive velocity direction. And then now we're saying that object is going to be moving upward. So my velocity is upward, but my acceleration is in the negative or downward direction. And so if we just think back to our basic vector addition, these vectors are in opposite directions. And so mathematically, instead of combining for larger values, they're going to work against each other. And so it's going to take that velocity value and it's going to make it smaller as that object is trying to move up towards the sky. Now, you should understand from your life experience that if we take this ball that the boy is holding and he tosses it up into the air, well, that ball's going to go up, 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 and then eventually it's going to reach its peak. This is going to be the highest point it will ever reach, and then from there, it's going to fall back down into the boy's hand, assuming that he tossed it straight up. And so that's what's going to happen to our objects for all of our questions as well. This object is going to come up, and then just for the briefest moment, it is going to pause or stop so that it can then change directions and fall back down towards the ground. Now, if we are still on Earth or some other planet, then we still have our acceleration. My acceleration is still going to be in the negative or downward direction, but now my object is already moving in the negative direction. The acceleration is also in the negative direction. So this is why my objects are going to move faster and faster as they fall. Now we have already discussed this part of the motion. We've already talked about the object having the velocity of 0 at the absolute highest point that it will ever reach. And then you guys often can tell me without me even teaching you this, that objects are going to move faster as they fall. Well, that's because they are accelerating so that the velocity and the acceleration are in the same direction. And so that just makes my speed larger and larger and larger, okay? What we're going to focus on today is comprehending what's happening on the first part of my drawing. If my object is moving in the positive or upward direction, but my acceleration is in the downward or negative direction, then my acceleration is going to cause my object to decrease in speed as it is moving up towards the sky. Eventually, it's going to decrease so much that the object is going to come to a complete stop. And so that is when it then begins to fall back down towards the ground, okay? So we've got to remember some basic vocabulary. Acceleration is the rate of change in velocity. So my velocity is changing as time goes on. How is that velocity changing? It depends on the direction of the object, but my acceleration rate is always going to be a negative 9.8, no matter what we do with our object along that vertical axis. Okay, so now we have an illustration here that has some values for us, and I just want to take a moment to look at some of the numbers that they've provided for us, and let's just draw some conclusions here. We have a velocity of positive 20. Now, we won't normally write that plus sign in front of the number, but to illustrate and emphasize that this is a positive value for my velocity, this means that my object is moving in the positive, or since we're on the vertical axis, then that means this is in the upward towards the sky direction. You can see that my object is then going to have a velocity of only 10 meters per second. So these are 1 second intervals in our drawing. They are showing us where the object is located every second. So at 0 seconds, at the moment that the boy is getting ready to throw the ball, it does not have any time on the clock, but we throw it up with a velocity of 20 meters per second. Now the clock starts. 1 second later, Here is my object. This is a velocity vector that they are drawing for us in this particular picture. And you can see that the visual representation is that the length of the arrow is shorter because the velocity is less. That is exactly what is happening. My object is slowing down. Now, when we get to this location, you can see that I have a velocity of 0. Notice they did not give me a vector here because the velocity value is 0. There is no vector to draw. My object has continued to change its velocity and has ultimately reached a value of 0 meters per second. Now, when we introduced the concept of free fall, we said the velocity at the top is always going to be 0. And that's what we have here. When my object reaches the highest point, that velocity is indeed 0. Now, because gravity is still acting on my object, it is still accelerating, we have a velocity value of negative 10 meters per second. Gravity's continuing to work. Acceleration is constant, which means we're just going to keep changing it by that same interval. So you can see from the illustration that they have taken our negative 9.8 that we'll be using in our calculations, and they've rounded it to 10, so we have nice, pretty numbers to look at. So we are decreasing our speed by a value of 10, and now we are going to be increasing our speed by a value of 10 because that's what it means to have that acceleration rate. Notice that the direction is now downward, so my velocity is a negative 10 because the object is physically on its way down towards the ground. You can see that in the next moment, my vector is longer than it was before because it is continuing to change its velocity so that now it is moving downward with a greater speed, and we are back up to a speed of 20 meters per second, but now my object has a negative velocity because it is physically moving downward towards the ground. Okay, so let's just kind of make some conclusions about the patterns that we see. Obviously, it's changing by our negative 9.8 rounded to 10. It's changing by an acceleration rate due to gravity. But I also want to point out to you, at the highest point, the velocity is 0, but notice that both of these objects are at the same physical, or this object at these two moments is at the same physical vertical position from the boy's hand. So if we look at our displacement, we can see that we have a displacement of 15 meters and 15 meters. So when the object is 15 meters away in this particular situation, it has a speed of 10 meters per second. When it's vertically on its way up, it has positive 10, and when it's on its way down, the velocity is a negative 10. When my object returns to the boy's hand, we are now at the same vertical position from the boy's hand. We see that these velocities are once again the same magnitude, but one is positive when it's on the way upward and one is negative when it's on the way downward. And then notice here that my displacement is a value of 0. Remember, in our kinematics equations, this D stands for displacement, which is the change in position where we're comparing the initial and the final position. So if the ball vertically returns to the same height as the boy's hand where it was released from, then it's back to the starting point. And so we have a displacement of 0. So we have discussed in detail that displacement is going to be positive if the object is above the starting point. So please be careful. We don't want to say that the displacement is positive or negative because the object is moving up or down. That is incorrect. It is based off of that initial reference position. So both of these locations here are located on the y-axis on the positive side, physically above where it started. So both of these displacements are positive. Our displacement will be negative if my object is below the starting position. So in this particular illustration, we do not have any negative displacements because in this drawing, the ball never physically moves below the boy's hand. If he does not catch the ball and the ball continues to fall, now we will begin to see negative displacements. Now we're going to take a moment and we're going to look at the times. If we look at how much time it takes to reach the top, to reach the peak, the highest point, the maximum vertical displacement, these are all phrases that you are going to see in the questions. They all mean the same thing. The amount of time that it takes for the object to get here. That's what I'm talking about, okay? So if we look at our picture, the ball has gone through half of its motion. It started at 0 seconds. Once the ball gets put into motion, 1 second later, 2 seconds later. So it took 2 seconds for the ball to reach the highest point. And so we are going to say that this is my time to the peak, my time to the top. This is the time to the maximum displacement, maximum vertical displacement. There's lots of different phrases that we can use here. Now, if we evaluate how much time it takes for the ball to go from this vertical position back to its original vertical height where it started, you can see that that also took 2 seconds of time. So it's 3 seconds, 4 seconds in total for my object to return to that same vertical position. So we would say that my object spent a total of 4 seconds in the air. Sometimes you will see this referred to as hang time. And that's a phrase that a lot of times students don't know what we're referring to. Hang time is the total time, okay? So in this particular example, my object had a total time of 4 seconds in the air. The time that it took to reach the peak or to reach the highest point was only 2 seconds. Well, if we think about that, a total time of 4, time to the top of only 2, that's half of the time. So we are sometimes going to also refer to this as our t half because it is only halfway through its physical motion. Now, you are going to get questions where we only ask you about the ball traveling to the top, and then that's the end of our question. So you're going to have to make sure that you understand what is happening in this situation and what part of the motion are they asking us to analyze. We are not saying that the object is going to stop here, like in real life forever. It's not going to stop here, but momentarily it comes to a stop. And so we often use this moment, this midway point, as a location that we're going to use to ask you a variety of questions. So when we talk about our time, we now need to be careful. There is the total time, which is the time that it takes for the object to go up and come back down. And then we're going to have the half time, which is to the peak or to the top. And this is just to allow the object to reach that highest point, and that's it. So you're going to need to evaluate, am I supposed to use the 2 seconds or am I supposed to use the 4 seconds? And it just depends on what part or parts of the motion you are being asked to analyze in that particular situation. Okay, so I also want to talk to you for just a moment about the difference between answering questions on speed versus velocity. You are supposed to know that speed, let me not use an arrow, that could be confusing. You are supposed to know that speed is a scalar vector where all of your answers are going to be positive numbers. And this is just the magnitude. This is the how fast, and that's it. Okay, we are going to measure it in meters per second. Now, we've learned that velocity is the vector version of it, which means that it includes direction. And so because it is a vector, it could either be positive or it could be negative numbers. We're also going to measure that in meters per second. So when you are looking at your questions, you need to pay attention to what is it asking. Is it asking me for the speed or is it asking me for the velocity? Now, sometimes students overthink this a little bit too much. The equations are set up to solve for velocity. as a vector. So do the math work, solve for your velocity. If you calculate a negative velocity, put that as your answer. If it's something that I'm going to grade by hand, if I need that negative to be there for full credit, you will have it. If I do not decide to consider the negative as to whether or not you're going to gain or lose credit, then it doesn't hurt anything to have it there. But if you choose not to write the negative, and this question is worded so that that negative is worth points, you definitely don't want to leave it off. So always write the negative if that is what you calculate, okay? Okay, so then it's saying here that we are going to look at the speed versus velocity on this particular illustration. What I want to point out to you is right now it shows you the speed. How do I know that? Because there are no negatives. The speed of my cannonball at the moment that it leaves the cannon and then at the moment that it returns to the same vertical position, it went up and came back down. Notice that those speeds are the same. If we are evaluating the velocity of our cannonball, we would have positive numbers for the first half of its motion, but here it's on its way down, so this technically should be a negative 10 if the question wants velocity, a negative 30 for velocity, and a negative 50 for velocity. So here is a unique question that you are going to see in the future. If we are asking you to let an object go up and then come back down, and we want to know how does the initial velocity compare to the final velocity, I want you to tell me that the initial velocity and the final velocity are going to be the same magnitude. What does that mean? That means the absolute value of these two numbers are going to be the same. So for this example, it's a 50 meters per second for the initial velocity, and it's a negative 50 meters per second for the final velocity. But if I'm just comparing the speeds, that's a 50 and a 50. Now, we do need to understand that that final velocity must be a negative number if my object is on the way down. And for these kind of questions, that will be the case. So my initial velocity is going to be a positive 50. My final velocity is going to be a negative 50. And so this is just a fact, a conceptual thing that I need you to know about objects that go up and then come back down along that vertical or y-axis. All right, we're going to work through a couple of questions here. We have a chart. In your practice package, you guys will have the full sheet of paper where there's an illustration to go with it. But basically, I just want to make sure we understand how to use the formulas in order to allow us to calculate these values. So we are going to start off by calculating our displacement, okay? So I've already put on the screen for you. This is the equation that we want to use, and whenever I pull my notes into Notability, it just doesn't always handle that font correctly. So let's change this real quick, and instead of this being t times 2, that is incorrect. It's supposed to be t squared. So make sure you are knowing the difference between these whole numbers that we're multiplying by and then our exponents. Okay, so for this particular question, if they are asking me what is the displacement, and the first missing number here is right here on our data table, and this would be at a time of 1 second. So we have a situation where our object was thrown. You see that we have a velocity here of 30. So this tells me that my object was not dropped. It was actually sent with a velocity to begin its motion, and because this is a positive number, this tells me that my object was sent vertically up into the air. So I am going to have an initial velocity of 30 meters per second, not 0. We got to make sure that we do things based off of facts and not based off of habit, okay? So This object is moving vertically through the air. It is going to be affected by gravity. So the acceleration caused by gravity is a negative 9.8 meters per second squared. And then we are going to figure out what is the displacement after 1 second of time. So I'm going to go ahead and list a time of 1 second. So we have D equals VIT. So I'm going to put my VI of 30. I'm going to put my time of 1 second plus 1/2. Now, I don't want to mess with decimals here. I want these numbers to be real nice and neat so that you can clearly see the pattern. So I'm going to go ahead and choose to round our 9.8 to 10 for right now. So we're going to say times acceleration due to gravity. We'll use a negative 10. And then times my time squared. So if I take all of this information and I put it in my calculator, this gives me a value of 25 meters. So I'm just going to put 25 meters right here on my data table. So after 1 second, my object has traveled 25 meters. Then I'm going to calculate what would my displacement be if we now had a time of 2 seconds. So now we're going to figure out this value here. So D equals, my VI is still 30. Look at my list of givens, or remember that this was an object that was thrown up into the air one time with a speed of 30 meters per second, sending it upward, okay? So now we're going to say times 2 seconds plus 1/2, we're going to round gravity for pretty numbers here, times 2 seconds, and then that 2 is being squared. So when I put all of this in my calculator, I get a displacement of 40 meters. So I'm going to put a 40 meters here. And this is the idea behind how we would go about figuring out what our displacement is. Now I'm going to choose not to work all the problems with you. I'm going to go ahead and fill in some of the remaining numbers. So when we get to our time of 3 seconds, I would calculate a displacement of 45 meters. Now I want to pause here and I want to point out all of these displacements are positive because in real life this object was thrown up into the sky, and so it's 0 seconds here, 1 second here, 2 seconds here, 3 seconds there. That's how this works. So it's getting farther and farther away from its initial release point, but now we are at the highest position that it's ever going to reach, and I'll come back to that in just a second, but all of these values are positive because all of these dots have my object above its starting point. So positive displacement because it's above the starting point. Now, if we look at our data table, they have already filled in for us that we have a velocity of 0 at this location. You are responsible for understanding that the velocity at the highest point is always 0. So the fact that we have a velocity of 0 at this location tells me it's not going to go any higher. Now it's going to begin to fall. And so if I were to plug the numbers into my formula and do 4 seconds of time, I would now calculate a displacement of 40. And I'm going to show you that it works that way. So 30 is my initial velocity. We'll do 4 seconds of time plus 1/2 of gravity. And our time right now is 4, and that is being squared. So if we were to do the math work here, 30 times 4 gives me a value of 120, and then 1/2 of negative 10 for this example times 4 squared gives me a value of negative 80. When I add those two numbers together, I do indeed end up with a value of 40 meters per second. And notice that it's a positive 40. Why is that? Because as the object falls back down, it is still vertically above the starting point. So all of these values here are going to be positive numbers. And then eventually we get back to where we started. Let's take a look at our velocity. We started with a velocity of 30 meters per second. It took us 3 seconds to get to the highest point. which means it should take another 3 seconds to get back to our starting position. There we are with a displacement of 0. And if we went vertically upward with an initial velocity of 30 meters per second, when we return to that same vertical position, it's the same speed but negative, because now my object is physically traveling downward towards the ground. So it's a negative 30 for my velocity. Now if I continue to calculate my displacement, let's go ahead and calculate what our displacement would be for my 7 seconds. So my initial velocity is 30. It was thrown up into the air one time with that speed. And then we're going to say times half of gravity. And then 7 is the value that is being squared. So if I put all of this into my calculator, this gives me a value of negative 35 meters. Now, this is our first negative displacement. It is negative because my object was on its way down. It came back to the displacement of 0, but it continued to fall. So now my object is located below where it started. That's why we have a negative number here. Okay, so this is how we go about calculating. Now, these questions where we're filling in the chart and we're just 1 second, 2 seconds, 3 seconds, this is really for the repetition, and it allows us to analyze the trends and some of the main ideas that we need to understand that are going to allow us to be able to address the word problems in the future. In the future, you're going to get a story, and it's going to tell you that this boy threw a rock up into the air with a velocity of 30 meters per second. What is its displacement after 7 seconds? And that's all you're going to get. So I'm showing you how this plugs into the formula. Now, what if they were asking me what is the velocity of the object after it has been in the air for 8 seconds? Well, based off of the conversations we've already had, I fully expect you to be able to recognize the pattern and predict that just from the chart. But again, in the future, you're not going to have a chart. So if we are trying to find the final velocity, is the rock done moving? I don't know, but it really doesn't matter. It's asking me after this much time. So this is a later moment, so it's going to serve as a VF for us in our equation. So now, if my VF is my unknown, and I'm trying to do this for 8 seconds of time, then I can use this equation to figure out what that final velocity is. So VF equals VI plus AT. So for this question, I'm looking for VF. My VI is 30. Don't put in a 0. That's not the situation for this question. We'll go ahead and stick with a negative 10 just so that we continue to get pretty numbers for right now. And we are at a time of 8 seconds. So when I plug all of this information into my calculator, it sure enough gives me a velocity value of a negative 50 meters per second. And if I look at the data table, that is what that next value should be. So this is how I want you to go about handling these types of questions. All right, we're going to go ahead and just look over some summary information, basically. So here it says that we have an object, and from the picture, I guess there are no words, it shows that my object starts here and it goes straight down. So this is an object that has dropped what we initially started doing. I need you to know velocity at the top is always 0. So in this case, my initial velocity is 0 meters per second. My object is going to accelerate downward because of gravity. And so that's going to make my acceleration rate a negative 9.8 meters per second squared. When we look at our next example, we have an object that is thrown up into the air. Now, my object is not going to physically stop here and that be the end of the story, but maybe that's all they ask me about for this particular question. So here, we're supposed to know that when it gets to the highest point, the velocity is 0. And so we're just simply asking you, what is the velocity at the top? It is 0 meters per second. Now, when we start doing the actual word problems, we might find that needing to know this value of 0 is going to be essential for having enough information to plug into our equation. So we're just reviewing that main idea right now. Again, it's accelerating because of gravity, so we will once again use a negative 9.8 meters per second squared. Now, I haven't emphasized this, so let's just pause. The object is physically on its way upward. So the initial velocity would be some positive number. but the acceleration due to Earth's gravitational downward pull is still going to be a negative 9.8. Always, 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 it is negative for that gravitational acceleration. Then here in the last situation, we have an object that is thrown up. Once again, when it gets to the highest point, that velocity is 0, and so that's all we're asking you here. Velocity at the top is 0 meters per second. Now they're showing us in the drawing that we have an initial velocity of 30 meters per second when it begins its upward motion. And then we know that the object is going to return. And so they're asking us, what is that final velocity? Well, this is one of those facts, conceptual things that I said you're going to need to know in the future. If it has an initial velocity of a positive 30 and it is sent up into the air, it comes back to the same vertical position, then the final velocity on return is going to be the negative version of that speed. Okay? All right. What is the source of acceleration for these objects? That is gravity. Oh, I don't like that. Sorry, let's try again. All right. What is the constant value? In other words, what number are you going to be using in all of your math work? And it's a negative 9.8 meters per second squared. The direction is downward. It does not matter what my object is doing. Gravity is always downward. That's why it's always a negative. How do VI and VF compare for objects that are dropped? Here it says in true free fall, I want to know objects that are dropped objects. So for my dropped objects, we are going to have an initial velocity of 0, and then we're going to have a final velocity, which is going to be some negative number. So what does that mean? That means that my VF is always going to be larger than my VI. Remember, you can't have a number less than 0, so negative numbers are not less than here. They're just going to be greater magnitudes, but in a downward direction. How do VI and VF compare for objects that are thrown straight up into the air? VI and VF for objects thrown straight up into the air. Well, we need a little bit of clarification here. If the question is asking me to let the object go up and then come back down to that same vertical position, then my VI and my VF would be the same magnitude, but my final velocity would be negative because it's in the downward direction. So same magnitude, but negative for the VF. Describe the velocity of an object that is moving upwards. Now, when our objects are moving vertically upwards towards the sky, I need you to understand that those have to be positive velocities. Those have to be positive velocities. So my object is going to have a positive velocity because it is moving in the positive direction. But the object is going to be slowing down, or we could say that it's going to decrease in velocity, okay? You need to be familiar with the different ways that we can word these situations. All of that means the same thing. Describe the velocity of an object that is moving downward. So if it's in the downward direction, that has to be a negative value for the velocity. So we would have a negative velocity. And the object itself would be speeding up. Or we might say that there is an increase in the velocity while it is moving in the negative direction.